Hi everybody. So, in the last lecture we have given a summary of how multi-dimensional data can be processed by a CUDA program and how threads inside a thread block can synchronize among each other. While discussing that, we also talked about, of course we have discussed this earlier also, that in GPU program execution there is specifically for CUDA program execution we have this concept of warps. So, basically that would mean which are the threads that are going to execute together in lockstep, at least from the programmer's point of view, even if not from the hardware's point of view. So, we will from this lecture we will discuss in more detail with respect to that how the GPU essentially is going to schedule the threads in packets of size warps, and what are the performance issues that can actually occur if the programmer is not aware of the way the program is going to be scheduled. So, just to do a summary here, so the topic is warp scheduling and divergence, and this is our week 5 topic here. And so, doing a summary of overall GPU architectures, if you remember that the GPU can be viewed as an array of streaming multiprocessors, where each SM, the streaming multiprocessor, has the following elements. It has got a large register file that can be partitioned among the threads for execution. So, it is basically partitioned across the SMs, the SPs, the scalar processors inside the SMs. Inside the SM, apart from having a large register file, you also have these several types of cache. For example, you have a piece of memory segment which can be partitioned to behave as a shared memory, and also a part of it to behave as an L1 cache, referred to our earlier lectures on GPU architecture for this. And also inside the SM you have got separate cache memory areas for storing constant values to be used inside a program, the constant cache and also the texture cache. Also, each SM inside it has got a specific piece of hardware which is called the warp scheduler, which is going to decide which threads are going to execute when inside the SM. The actual execution units comprise the scalar processors, which contain the integer ALU and the floating point unit, along with as a separate unit, not as a part of the scalar processor. You also have special function units present inside the SM, which are responsible for computing the transcendental functions, for example trigonometric functions. Now, just to review the different data types and you use inside your CUDA programs and their corresponding scopes that get decided based on the way in which you declare the variable. So, as long as your variable is not an array variable, is an automatic variable, its the scope is a thread. So, it's basically it's going to be stored in a register. It's not an array variable, it's going to be stored in a register as long as registers are available. Its scope is part thread, and the lifetime of that variable is the execution of the kernel. So, if you have a local variable v which is going to be used by every thread, so every thread will see its own copy of this variable and with a corresponding mapping in one of the registers, right. If you have an array variable, for that also the scope is thread. Every thread will see its own version of that array variable if it's declared inside the kernel as a local array variable. The memory type is local. That means it will be stored in a segment of the DRAM which is reserved for the execution of this thread. Of course, since it's part of the DRAM, it's a local memory in terms of in the parlance of the programmer, but physically it's located far away, so the access is slow. Again, the lifetime is that of the kernel. If it is declared as shared, then the place where this variable will be mapped physically is the shared memory segments of the SMs. The visibility will be the block. That means all the threads inside a same executing thread block will have a consistent view of this variable, which is defined as a shared variable. The lifetime is again the kernel. That means as the moment the kernel finishes its execution, this variable's scope is lost, right. And then if we declare a variable as a global variable, if we declare the variable as a global variable, then I mean the way you declare is you simply have it as a variables type as a device type variable without the annotation of shared or something. So, that would actually infer it as a global variable. It will be resident in the global memory, and then the scope is actually grid. That means the variable is alive across the different across the entire execution of the application, that is it is alive across multiple kernel instances as operated from the host program side. If the variable type is defined as constant, then its location is in the specific constant memory location of the memory hierarchy of the GPU. Again the scope is grid and its lifetime is the application. That means it is consistently accessible by multiple instances or multiple different kernels. All of them are assumed to be controlled by the same host program. So, one application is one host program can comprise multiple kernel launches. So, for such scope, that is grid, the variable has to be of type global or constant. Its definition should, for constant, it should have a constant keyword. If nothing is there, it is inferred, but the type is device, then it is inferred as a global variable. Type is device and you have the shared connotation, then it is defined as a shared variable. But with shared, as we know that the scope is the block, all the threads inside the thread block will have a consistent view. Lifetime would be kernel, and also for normal array and non-array type variables, depending on whether it is array, then the memory is local. If it is non-array, a single instance, then the memory is register. For both of them, the scope is thread. Every thread has a different copy of them located in their local memory, or the local memory is essentially the private memory corresponding to that thread in the DRAM, or the corresponding registers that the thread has been allocated, and again the lifetime is kernel. So, these are the different memory types and scopes that we can define for the CUDA device memory side. So, as you can see that these are all as long as it is a part of the shared or global or the constant type memory, the scope is specified explicitly with this device connotation here. Fine. So, with this, if we progress, now the question that comes is how really do threads get mapped to hardware. So, this is an example picture that we are trying to give here. So, we are trying to say that suppose I have defined threads in a way that I have blocks and each thread block contains m number of threads. So, we are trying to show a sample mapping here where we are trying to show multiple SMs. So, this is SM0, this is SMK, in between we have with the dots we are trying to represent there are a lot of other SMs in between. Inside each SM we are trying to give a figure that how the register file is logically partitioned for the SPs, that means for the threads to do their computation privately, some part of the register is blocked for each thread to do their computation, store their automatic variables and all that, and each thread is mapped to each of the SPs. And so, if I have a thread block, then the threads in the block are getting mapped to one specific SP like this. We are just trying to show a possible mapping. Now, of course, the question may come that suppose I have more than this n number of blocks, or let us say I have more blocks than there are SPs available inside an SM. So, then what will really happen? So, before going into those questions, just we are trying to give we are trying to recall one of the example mappings we discussed. So, this is an example of a 2D mapping here. So, we are trying to show that we have this many blocks in the 2-dimension space. For each block we have again threads which have been mapped into the blocks like this. So, this was one of our earlier examples. This is just again here for example purpose, and consider a generalized mapping scenario here. So, you have got this 20 threads inside each block, and you have got total how many blocks? You have got in total 18 blocks, right. So, you have 18 blocks and 20 threads here. So, or maybe we consider a mapping scenario. We have a set of blocks, and the block dimension let us say is 5, 4. So, that is you have 20 threads per block, and consider that you have 6 SMs together, and the total number of scalar processors per SM is 40. So, we are considering a scenario where you have an SM containing 40 SPs and you have thread blocks of size 20. So, what does that mean? That would mean that 2 blocks are mapped to one SM at a time. Why is that a good thing? Because your hardware resources are completely utilized. Why is that so? The reason is we have to remember this as a rule of thumb, that a block cannot be partitioned while mapping across SMs. A block cannot map half of the block to SM1 and half of the block to SM2. That is not allowed. So, as long as you have blocks, the thread block size which is like you have so as long as the scenario is like this, that you have a block dimension and the number of SPs in the SM is a multiple of that block dimension, you can block and you can have an integer number of blocks getting mapped inside an SM without any SP lying unutilized. So, that is a good mapping. So, with that example mapping, if we just instantiate the earlier picture, this here everything was in symbols. So, we are considering m number of threads, and these m threads we are getting mapped to this m number of threads per block, and we are considering n blocks inside an SM. So, in this example what is happening is we are having 2 blocks, right. So, we are having 2 thread blocks which are getting mapped to one SM here. Each thread block is containing 20 threads, right. Just to recall, here we had discussed that there would be 40 SPs per SM, and in total for each block there are 20 threads. So, that would mean for the 40 SPs we can logically partition them across in sets of 20, and we can map each block to one of the collection of 20 SPs, right. So, I have block 0,0 mapped to this nice collection of 20 SPs. I have block 0,1 mapped to this nice collection of 20 SPs like this for SM0. Overall, if I am considering 6 SMs, and then I can go on like this and map the other blocks, and since I have 6 SMs and I have got this these many blocks, these many thread blocks to map. So, I should be able to keep on mapping like this 2 thread blocks per SM, and in that way I would be having an execution of how many blocks. So, as you can see, 2 blocks are getting executed per SM. I have got 6 SMs. So, overall I have 12 blocks executing in parallel, right, inside this entire GPU system. Well, what about the other blocks? I had got 20 of them. The scheduler is holding them back because there aren't enough CUDA cores available to execute all of the thread blocks in parallel. Now, which is quite a general scenario. Your kernel dimensions, launch parameter dimensions allow you to launch a large number of threads. Of course, physically you may not have that many CUDA cores available across this hierarchy of SMs, but that does not matter. Your hardware scheduler takes care of mapping these thread blocks inside these SMs in kind of, this is an example packing I am showing with this kind of packings, and once some thread block will finish execution, some other thread block will actually get mapped into one of the SMs, and this way the execution will continue. So, consider this kind of a mapping in a resource constraint scenario. We consider a scenario where the resources of the architecture are limited. That means, say your grid dimension is like this. You have this grid dimension, and so and you have SPs per SM earlier that we have considered was 40, and now you are considering that you have grid dimension 6,2 just like earlier, and block dimension was 5,4 just like earlier. But now, instead of considering SPs per SM as 40, let us start considering SPs per SM as 20. So, what happens now? Since your SPs per SM is 20, at a time inside one SM I can execute only one thread block. So, there will be further serialization of execution of thread blocks, right. So, that would mean in one SM I have got only one block executing, right. In another SM I had got another block executing. So, with respect to the earlier example, I have got more number of blocks waiting to execute, because earlier I was executing more number of blocks per SM. So, earlier I was executing with these 6 SMs, I was executing 12 blocks in parallel, but now with these 6 SMs I am executing 6 blocks in parallel. So, the number of batches of thread block execution becomes larger and it is more sequential scenario, right. So, now I would have in this way less number of blocks executing parallel due to lack of hardware resources and more number of batching of thread blocks. So, this batching of thread blocks and decision of which block goes to which SM would be will actually be decided by a global hardware scheduler resident inside the GPU. Now, some general examples here, like so when we speak of these thread blocks, SPs and SMs, the maximum allowed thread block size is 1024. In modern architectures, it can actually become 2048. It is also a property of the architecture. Now, the reason is an SM can store maximum 1024 thread contexts. So, every SM will be able to it has to remember what are the threads that are mapped into it, even if the thread is executing or not, right. So, that is the context of the thread. So, that context needs to be stored, and this limitation on the overall thread block size actually comes from the hardware requirement with respect to storing this maximum number of thread constants, these thread contexts. So, of course, the SM can have less than 1024 SPs, but it does not matter. As we discussed that I do not really need to execute all the threads in the block in parallel. What the constant of 1024 or 2048 for that matter comes from the SM's ability to remember the context of the threads. It has been mapped a full block or maybe multiple blocks. It should be able to remember the context of the threads. If the amount of memory available is something finite, then only, I mean, in this case it is 1024 thread context, the amount of memory is limited by that, then only that many threads can be part of one block. So, because even with that setting, although the SM can have less than 1024 SPs, that means all the threads inside the block are not executing in parallel, but the SM can remember the context of the thread and actually schedule the threads using a smaller number of SPs by remembering the context of the thread. Okay, it executed up to this point, then some other thread, then some other thread, like that. We will see examples. So, if we look at an example of GTX 970, there are 13 SMs. So, overall it can actually remember 13 cross 1024 thread context in parallel, and however, it does not mean that many SPs are available. It has got only 128 SPs per SM, but it can remember that every SM can store this many the number of thread contexts in parallel, and accordingly it can schedule the execution of this maximum 1024 threads per block inside the SMs by suitably choosing the threads inside the block and packing them together for execution on the SPs. So, that is where the scheduler unit which is inside the SM will come into play. So, one block goes in one SM. One block cannot be divided across two SMs or more SMs. One SM can have multiple blocks. If an SM can store maximum 1024 thread context and block size is 256, we have 4 blocks per SM. So, 1024 is giving you the maximum block size that is allowed, and of course, you are free to actually define a block size that is less than that. But since the SM can store at max 1024 thread context, and if you give a block size of smaller size, let us say 256, then when you are going to launch your kernel, that SM can be mapped with 4 thread blocks. Your block size is 256, this is important. Your block size, suppose you have chosen to write a program where you have launched a kernel with block size 256. Since the SM can store maximum 1024 thread context, that means it can remember the context of these many executing threads while executing a subpart of them in parallel as defined by the number of SPs, but still, since the max is 1024, your block size is a smaller value 256, the SM can be mapped with 4 thread blocks. 256 times 4 is 1024, and this mapping is decided by the high level scheduler who is distributing the blocks across the SMs. So the number of blocks that will be mapped to the SM is defined by the number of threads per block, while remembering the total number of thread context that the SM can remember. So this is what the hardware scheduler decides. It decides which thread block will map to a collection of SPs or to map to which SM, and inside the SM we have a secondary this hardware scheduler which decides that okay, these are the thread blocks that has been mapped to this SM. Out of these thread blocks, which are the physical threads which would be packed together for an execution. This binding of physical threads together for a lockstep execution is what we have defined earlier as a warp. So this is the basic unit of execution inside a GPU's SM. So this is done by the hardware scheduler block sitting inside the SM. So the SM will be assigned a set of thread blocks or maybe one thread block. Inside the thread block you have multiple threads. Which of the threads will actually execute in parallel in units of execution, that is warp, will be decided by the GPU's SM's hardware scheduler. So this is basically a way we are trying to give the picture. So we have an SM. Inside the SM you have this warp scheduler as a hardware unit. It is deciding which of the threads are going to be dispatched together to the SPs for execution in lockstep. So just to summarize, the warp is a unit of thread scheduling inside the SMs. Warp size is implementation specific. Typically it's still now 32 threads inside a warp. Now this warp is executed in SIMD fashion, that is the warp scheduler launches a warp of thread. Each warp typically executes one instruction across parallel threads. If a SM has 128 SPs, it can execute 4 warps at any given time. One warp has 32 threads, right? So the question is, what is a part of the warp? Which are the thread IDs that are the part of the same warp? That is what is decided by the warp scheduler sitting inside the SM. So just to view it here, the warp scheduler decides which threads to pack together for execution in a warp. These are all threads with consecutive thread IDs, but so the threads in the warp are guaranteed to execute the same SIMD instruction together. It executes one SIMD instruction followed by the next SIMD instruction in lockstep like that. Different warps can actually progress to the SM together. Why? Because I have more than 32 SPs. For example, I have let's say 128 SPs. So in parallel 4 warps may execute together. So inside a thread block I have lot of threads. These threads are packed into packets of 32 by the warp scheduler. These packets of 32 threads are what will execute in lockstep together from the programmer's point of view in terms of instructions, right? But again the warps may progress at different speeds. Each warp ensures that the threads inside that warp progress at the same speed, but I have different multiple warps can actually go in here, which is this, and which warp goes in here that is decided by the warp scheduler. So which are the real warps that are executing, it depends. That is why when I launch a thread block containing large number of threads, as we have discussed earlier, there is no guarantee that all the threads are progressing at the same speed. The threads will be packed into warps as decided by the warp scheduler, and it will decide which packet of threads will progress at which speed. That is why we will require the sync thread or some kind of synchronization primitive like that to ensure or force synchronization among threads, so that they actually have a consistent view of data points on which they want to collaborate and work together. With that, we would like to end this lecture and we will resume from this point. Thank you.